Hello to all, welcome to the channel Money's Gate Tech Vision. In this lecture, I am going to solve GATE 2025 problems from the subject electric circuits. For that, I have taken instrumentation paper. So the topics which I have taken is common for electrical, electronics and instrumentation. So those branch candidates can watch this video. Let me start the problem. So this is the first problem. Here, AC network is given. For the circuit shown in the figure, the active power supplied by the source is. We need to find the active power supplied by the source. AC network is given. We need to find the active power. Okay. So, we know the active power. So, active power equal to active power supplied by the source P equal to VI cos phi. So already supply voltage is given. Supply voltage is it is given. And we need to find out the current value and also the phase difference phi between the voltage and current. Then only we can find out the active power. So for that, first I am going to find the impedance equivalent impedance of the given network. So here, by observing the network, this resistance and capacitance are in series. This series combination are in parallel with this inductance, and it is in parallel combination and it is in series again. That equivalent is in series with the this resistance and capacitance combination. Okay. So now we have to find the Z equivalent. We'll find. So impedance equivalent equal to first phi minus J phi in parallel with the inductance J phi, the whole equivalent in series with 10 minus J10. Okay. By using that, phi minus J5 into J5 by phi minus J5 plus J5, and it is in series with 10 minus J10. Here this will get cancelled and this phi and numerator phi gets cancelled, and then J5 plus phi plus 10 minus J10, which is simplified as 15 minus J5. Okay. So phi is taken as common, phi into 3 minus J. 3 minus J. Okay. So 5 into 3 minus J is Z equivalent. So when we find the magnitude and phase angle, magnitude of Z equivalent equal to pi into root of a square plus b square. So 9 plus 1, 10, pi root 10. And phase angle of Z equal to tan inverse b by a. So tan inverse minus 1 by 3, which is approximately minus 18.43. Okay, the angle is minus 18.43. This is taken as pi. Pi is the phase difference between the voltage and current. So now we need to find the current. Okay, so current equal to V by Z, modulus of V by modulus of Z. So 100 is voltage value, modulus of Z, modulus of impedance is pi root 10, and here we can cancel 20 by root 10, that is nothing but 2 root 10. Okay. Now let me find the active power supplied by the source. So voltage magnitude is 100 and current magnitude is 2 root 10 and cos of minus 18.43. Okay. So cos of minus theta is cos theta only. So on calculation, it is approximately equal to 600.017. So here they have given rounded off to 1 decimal place. So if we round up, it will be equal to 600 watts only. The active power supplied by the source is 600 watts. So answer is 600 watts. 600 watts. Okay. 600 watts is the answer. So answer they have given from the range of 590 to 610. So 590 to 610 range is correct only. Let me move to the next problem. So this problem is given from the topic transients. Given from the topic transients. In the circuit shown, the switch is opened at t second. Open at t equals 0 second. Okay, this is t equal to 0 second. The current at 2 millisecond is dash milliamps, rounded off to 2 decimal place. Okay, switch is opened at t equal to 0 seconds. So initial condition is closed condition and final condition is open condition. We need to find the current value at 2 millisecond. So they have given t value at t equal to 2 millisecond. What will be the current? So here we have to find out the current I of t which is flowing through 120 ohms. Okay. So this will be taken as IL of t. Current flowing through the inductor. But in this problem we need to find out the current passing through 120 ohms. Okay. We need to find out the function for the current passing through 120 ohms. So let me find out from initial condition. So starting from the initial condition. So what is the initial condition? At t equal to t less than 0. That means t equal to 0 minus switch is closed condition. So when switch is closed, the initial condition itself, it attains the steady state condition. Okay. So when it attains the steady state condition, L becomes short circuited. So when switch is closed, the circuit will be like this. Circuit will be like this. Okay. So this is short circuited. That attains the steady state. So it is short circuited. And here 10 milliamps. So in this short circuit, current will be directly flowing through this short circuit. There will be no current flowing in this direction. So this direction circuit can be discarded. Only the full current will be flowing through this part only. So we can mark the current value as, this is current value at 0 minus. Okay. Current flowing through 120 ohms at t equal to 0 minus. So we can mark I of 0 minus is 0 milliamps only at the initial condition. There will be no current flowing in the right hand side direction. Full current will be flowing in the short circuited condition. Okay. This short circuit. And then next, this is first point. And then next time, immediately after the switching condition, the time immediately after the switching condition, that is at t equal to 0 plus. But switch is opened. Okay. Switch is opened immediately after the switching condition. That means due to the inductor, now IL of 0 minus is also equal to 0 milliamps. And we know IL of 0 minus equal to IL of 0 plus. That means it is equal to 0 milliamps. So immediately after the switching condition, the current flowing through the inductor will be 0 milliamps only. So, but switch is in open condition. So the circuit will be like this. This is in open condition and current source. And this is resistance 50 ohms, 100 ohms, and this is 120 ohms, and again this is 40, and this is 40, and current flowing through inductor is 0 milliamps. We can mark this as 0 milliamps. So when this is when I equal to 0, this whole part can be discarded. Okay, this whole part, there will be no current flowing in this loop. Flowing in this loop, I equal to 0 only. So we can discard this whole circuit. Okay. So this is 10 milliamps. So we can discard this whole circuit. So when we discard this whole circuit, only we are having current source 50 ohms, 120 ohms, 100 ohms. So all the resistance are in series condition. So obviously I of 0 plus will be equal to the full current will be flowing through the 120 ohms. So we can mark I of 0 plus immediately after the switching condition. The 10 milliamps, the total current will be flowing through the 120 ohms. Okay. So this condition also we have found out. And then at t equal to infinite condition. At t equal to infinity. Okay. So this is final condition. This is final condition. So at the final condition, switch is opened only. Switch is opened only, but steady state, it is otherwise called a steady state condition. At the steady state condition, L should be short circuited. L should be short circuited. So the circuit will be like this. Circuit will be like this. It is in open condition. Current source, and then resistance, and then here 120 ohms, again two resistance. Here L should be short circuited at the final condition. This is short circuited. Okay. And we can mark the values 100 ohms, and this is 120 ohms, and 40 ohms, and 40 ohms. Okay. So here this 120 ohms, 40 ohms and 40 ohms are in series condition. 10 milliamps. So 10 milliamps is flowing through 50 ohms, and here we can mark I of infinity. Okay, I of infinity. Now by using current division rule, we can find out the I of infinity. So by the current division rule, the total current I of infinity, that is the current passing through 120 ohms, total current is 10 milliamps into opposite resistance is 40 plus 40, 80, and total resistance is 80 plus 120, 200. So 4 milliamps. This is the final current. So we need to find the current equation. Okay. The current equation can be written as, current at the final condition minus I of infinity minus I of 0 plus into e power minus t by tau, where tau is time constant. Here, since this is a RL transient circuit, L equivalent by R equivalent will be the time constant. So, since we are having only one inductance, we can mark point to as L equivalent. Now we need to find the R equivalent. So, to find the R equivalent, the current source can be open circuited. If the current source is open circuited means what will be the condition? Only this part we will be having. Okay. So if it is open circuited. So 120 ohms, 40 ohms, 40 ohms. All are in series condition. So 80 plus 120, 200 ohms. Okay. 200 ohms. So we can simplify this 0.1 by 100, which is 1 millisecond. Okay. 1 millisecond. Now we should use this formulation to find out the current at t millisecond. Okay. So let me find. So here I of t equal to, what is I of infinity? We have found out that 4 milliamps. And then again 4, and I of 0 plus is, already we found out I of 0 plus is, that is immediately after the switching condition we found out as 10 milliamps. So we will substitute that 4 minus 10 milliamps into e power minus t by tau, minus t by 1 millisecond. Okay. Now I of 2. So they have asked the current at t equal to 2 millisecond. So when we substitute t equal to 2 millisecond, 2 by 1 e power minus 2. So 4 plus 6 e power minus 2. So when we calculate this, it will be approximately equal to 4.81 milliamps. 4.81 milliamps. So the answer is 4.81 milliamps approximately. Okay, 4.81 milliamps for this transient circuit. Thus, we found out the current value at t equal to 2 millisecond. Shall we move to the next problem? So this problem is given from the nodal analysis. In the circuit shown, the galvanometer has an internal resistance of 100 ohms. The galvanometer current Ig is dash microamps rounded off to the nearest integer. Okay. So here for this, we need to find the galvanometer current. Galvanometer internal resistance is given as 100 ohms. Okay, first we should find whether the Wheatstone bridge is balanced or not. So, we should find whether the Wheatstone bridge is balanced or not. If it is balanced, means galvanometer current will be 0 amps only. Okay, so how we can find out the balanced condition? The opposite arms impedance product, the opposite arm product equal to another opposite arm product. That means if we take this is R1, R2, R3, R4 means that R1, the product of R1, R4 should be equal to R2, R3. Now find the product. This is 1000 into 1000 and here 1000 into 1010. So it is not equal. So it is not in balanced condition. It is unbalanced. It is an unbalanced bridge. So we need to find the current value. It is some microamps only. We need to find the current value by any of the method. So here I am going to use the nodal analysis method. Nodal analysis method. Okay. So I'm going to redraw the circuit. So this resistance is internal resistance. Okay. This is 4 volt and this is grounded. Okay. And here this is 1000 ohms and here 1000 ohms and here 1000 and here again 1000 ohms, 1010 ohms. So we are having two nodes. I am marking that as A and B. Okay. Now voltage at the node, I am marking that as VA and VB. Now I am going to apply the nodal analysis to find voltage A, VA and VB because Ig is the current flowing through galvanometer. It is given in this direction. So this Ig is nothing but VB minus VA, that difference of voltage, depends upon the polarity. Difference of voltage by 100 ohms. Okay. So for that we have to find out the two nodal voltages. So let me apply the nodal analysis method. So at node A, VA minus 4 by 1000 plus VA minus VB by 100, middle branch 100 plus VA, this is grounded voltage. So VA by 100, VA by 1000 equal to 0. So it is simplified as, taking the LCM, it is simplified as 6 VA minus 6 VA minus 5 VB equal to 2. So this is the first equation, first nodal equation from at node A. Let me find the second nodal equation. Now at node B, at node B. So this is see here at node B. Node B, we can write the equation VB minus 4 by 1000 and VB by 1010 and then VB by 1010 and then VB minus VA by 100. Okay. VB minus VA by 100. So VB minus 4 by 1000 plus VB minus VA by 100 plus VB by 1010 equal to 0. So this will be simplified as minus 1010 VA plus 1211 VB equal to 404. So this is the second equation. Okay. Second equation from the nodal analysis. Now by using Cramer's rule, we will find the VA and VB. Now we will find delta. Delta equal to minus 6 and 5. Sorry, 6 and minus 5. And then minus 1010. 1211. So 1211 into 6. 7266 minus 5050. That will be equal to 2216. Okay. 2216. So this is delta. And then delta 1 by replacing the first column as 2 and 404 minus 5211, which is equal to 2 into 1211, 2422 plus 2020, which is equal to 4442. And then delta 2, that is delta 2 is second column should be replaced 2404, which is equal to 6 into 404, that is 2424 plus 2020, which is 4444. So what we need to find out? What we need to find out? IG. So IG is nothing but VB minus VA by VB minus VA by 100. Okay. Now VB is delta 2 by delta and VA is delta 1 by delta. Okay. Delta 1 by delta. So VB minus VA equal to delta 2 minus delta 1 by delta. First we will find. So delta 2 is 4444. Delta 1 is 4442. So 2 is the difference. So 2 by 2216. So 2216. 2216. So therefore IG equal to, see, IG equal to, we have to use this formulation, 2 by 2260 by 100, which will become like this. It is approximately 9.01 amps. 9.02 microamps. 9.02 microamps. So here they have given us rounded off to the nearest integer. So we can mark it out as equal to 9 microamps. So no need to put the decimal. Only 9 microamps is the answer. The answer for the given problem is 9 microamps. So these three are numerical answer type question. There is no negative marking for this numerical answer type question. So we can mark easily. Okay. So shall we move to the next problem? In this problem, we used nodal analysis to find the current through the galvanometer. So whenever the Wheatstone bridge is given, first find whether it is balanced or not, then go for further process. And this question is taken from the magnetic coupled circuit. Magnetic coupled circuit. See, they have given the circuit can be represented using its equivalent T model. So here, coupled circuit is given. and its equivalent circuit is also given. We need to find out this inductance and this inductance and this inductance. So since here, see the dots. See the dots. From the dots itself, we can find out the flux direction. The flux direction is in opposite direction. Okay. The flux is in opposite direction. This is in opposite direction. So flux is in opposite direction and the current is in opposite direction. This is I1 and this is I2. Its equivalent is already given. We need to find out this value. So if we take this as L1 and this as L2 and this as mutual inductance means it will be like L1 plus M and here L2 plus M and here since flux is in opposite direction, this is minus M. So when we find the values, so when L1 is taken as 3 Henry, mutual inductance is 4 Henry, 3 plus 4, this equivalent and this inductance is 3 plus 4, 7 Henry. And here, this inductance value, L2 is 2 Henry. So 2 Henry plus 4 Henry, this is equal to 6 Henry. And here, this in the middle one, minus M, minus of mutual inductance. So that will be equal to minus 4. L3 equal to minus 4. So the given L1 equal to 7 Henry, L2 equal to 6 Henry, and L3 equal to minus 4 Henry. See the first option itself, we got the answer L1 equal to 7 Henry, L2 equal to 6 Henry, and L3 equal to minus 4 Henry. So option A is the correct one. So thus we solved 4 problems from the instrumentation paper. This is Mani's Gate Tech Vision. This is the channel for engineering lectures. You can subscribe to the channel. You can view the lectures freely. Thank you very much for watching the video. If any queries means you can mail me. My mail ID is dmoneylecture@gmail.com. Thank you very much.